Okay, so now we have this bootstrap tool in our toolbox. And now this is going to allow us to generate estimates of a statistic from a population. And we'll do this through this, this bootstrap and this resampling technique. And so then when we come up with this estimate, the next logical question that we may want to ask is, how good is that estimate? How good is that estimate? And this is where confidence intervals are going to come into play. And so again, the bootstrap, right? We're going to sample with replacement. And again, the keys for our original, we're going to draw at random with replacement. And then when we resample, it has to be as many times as the original sample contained. So we can compare the sample to the resamples. Okay, and so that allows us to compare the estimates from there. So now let's look at a 95 bootstrap confidence interval. Okay, and so what does that say? So instead of thinking of returning a specific statistic as an estimate, what we can do is we can return an interval of estimates on that parameter, on that statistic. Okay, and so instead of saying the estimate is X, we can say that it ranges from a high of some value to from a low of some value to a high of some value. So we're going to give it interval, and the size of that interval is going to be based on this confidence. And we'll talk precisely what this kind of confidence in this 95% is going to be. And then there's nothing magical about this 95% bootstrap confidence interval. I picked 95 because typically we do p-values of 5%. So, but it really could be any percentage between 0 and 100 from here. And so the confidence interval, and again, I know I'm being vague. I haven't just defined exactly what this interval is yet. But the higher the level, the higher the confidence, the wider the interval is going to be. And we're going to see this. So I'm going to come back to this. So if we had a confidence interval of 98, which that's going to be wider, it's going to capture more of the data. And so basically what we're going to say, and we're going to see this in the demo, is that when we say we have a 95% bootstrap confidence interval, what we're going to say is when we run our resampling, when we do our resampling, 95% of the time, the estimate, the statistic is going to fall within the range of those parameters. Okay, and so if we want to say, 98% of the time, our interval captures the statistic. If we want to, if we want to say that it's going to fall within 98% of the time, it's going to be wider. We're going to have to capture more of the histogram from there. Okay, so that's why the larger the confidence interval, the wider the range is going to be. And so what we're specifically saying is that 95% is our confidence in the process that generated the interval. So specifically, what we mean is that what comes at the end, this interval, it's going to be a good interval about 95% of the time. And I'll be more precise about what good means in a second. Okay. Okay, so confidence intervals. Okay, so again, staying with our population, our San Francisco data. One bootstrap, and so this is again our resample because we're using our sample from our data, and then we're going to do that 1,000 times, and then we're going to get a distribution. Okay, and so now here's the thing. So that all of this is the same. This is the straight up classic bootstrap. All of this code is exactly the same from here, and so now we have our distribution. And so here, let me just restart this and clear the output. Run this again real quick. Okay, and so now what we're going to do is we're going to take, and so we saw from last time, right, when we did this experiment down here, we got this distribution. We got the distribution of our of our statistics. Okay. And so what we're going to say now is we're going to look at that. We're going to look at that distribution, and we're going to look at the left and right. And we saw it's kind of roughly bell curve shaped. And so we're going to take this 95% from the middle of our results. And so we're going to take the left and the right. And so since we're going with 95%, basically we want the 95% in the middle. So what does that mean for the tails? That means the tails is whatever's left over. That's going to be 5%. And it's going to be 2.5% on the left and 2.5% on the right. Okay. So we're going to take all of our medians, and we're going to get the left and the right percentile. So we're going to get the left edge and the right edge from there. And what we're going to do then is we're going to plot out that histogram like we had before. Okay. And what I'm showing here in gold is that range from the 2.5% to the 97.5%. Okay. And so that's our 95% confidence interval. And so because we have, with this San Francisco data, we have the ground truth. And so we can actually know what the actual truth is. And that is what I print out in the population median is colored in red. Okay, so that's the ground truth. And then our sample median we shown in gold, in blue. So that is kind of the sample from all of the sample median from all of our runs. And then the interval shows the confidence interval. So this is, this is all of the runs that fell between 2.5 percentile and 97.5 percentile. Okay. And so what we're saying is, that we believe that that our estimate is going to fall in that range 95% of the time. Okay. And so what does this process look like? Again, take a sample, use it many times to bootstrap, and then use the middle of the bootstrap medians as our confidence interval from there. Okay. And so putting all of that together, we get this process. And so this is just, this part down here, this is the part that you want to kind of keep as your reference. And this is the entire kind of bootstrap process from soup to nuts, from A to Z, from going from our original sample, calculating our original sample. Here's our original sample mean. And then we're bootstrapping from there, right? So we take our original sample from our population, and then we bootstrap off of that. The one bootstrap median uses the R sample. From there, we do it 1,000 times. We get the left and right percentile, and then we plot out the confidence interval there. Okay. All right. So what does this mean? All right. So now I want to kind of give a more formal definition of what we mean by this confidence interval. Okay. And so this is the confidence in the process that generated the interval. Okay. And what do we mean by that? We mean it generates a good interval about 95% of the time. And so what this graph is showing, here is that, again, and this is from the San Francisco data set. And so since we have the entire population, we can calculate the population median. And that is the line shown in red here. Okay, so this is ground truth. The red line is the truth. Okay, and because we have all of the data, we can run the sampling process, not the bootstrap process, because we have all of the data. We can run the sampling process just like we did before. We can take a sample, an original sample of the data, without replacement, okay, and with 300 samples, and then we can, with that sample, then we can we can run that 1,000 times and generate one of these lines, okay? So each one of these gold lines is showing a sample, a 300 sample, and then we bootstrap that, and then we run that. And the bootstrap process gives us this confidence interval. That gives us this range, right? And we set it for this example to be 95%. And so that is one of these gold bars here, is one trial. The 300, the bootstrap, generate the interval, okay? Because we have the actual data, we can do that process, the entire process, going from the original, a new 300 sample, then do the bootstrap, then generate a new confidence interval. And for this graph here, we did it 100 times, okay? So this is the equivalent, and this is not something we normally can do. This was the equivalent of doing 100 of these 300 samples, okay? And each one of those, because we get a sample, we go through the bootstrap process, generates a confidence interval from there. And so what we're saying about a 95% bootstrap interval is, so by comparing to ground truth, what we're going to say is that this interval, where the ground truth lies within this interval about 95% of the time. And that's what we mean about that it's a good interval. A good interval means that somewhere in that interval is the actual statistic, in this case, the actual median salary. Okay. And if you look at these trials, if you look at these 100 trials, you can see that the line, the gold line, is actually encompassing, oh, let me put this on percent so you can see bigger, sorry. You can see that it actually falls in most of the time. And if you look, where are the places where it's an outlier? We have it here, right here. So 1, 2, it looks like maybe this one, 3, 4. So again, this is all random, so it's going to be about 95% of the time. And so by actually looking at ground truth, we can see that it did generate the statistic, the interval, the ground truth was within that interval about 95% of the time. Okay, so that's what we mean when we say our confidence interval. When we say something has a 95% confidence interval, we believe, we have the faith in the process that generated it. The process that generated it, we believe that is going to generate an interval, a good interval that has the ground truth in it about 95% of the time. Okay. And so now you can see, kind of, now that you kind of get a sense of the definition, you can see that if we had a 99% confidence interval, right, that interval is going to have to be wider because we want to make sure that the ground truth gets captured, 99 out of 100 times. And conversely, if we had an 80% confidence interval, we're only making the statement that our process will generate an interval that will have the actual ground truth statistic about 80% of the time from there. Okay. All right. So that was kind of a lot to throw at you. Any questions about this? All right. Well, then let's look at another case example to kind of drive this point home. Okay. So what we're going to do is we're going to shift data sets from the San Francisco population data to, we're going to come back to a data set that we've looked at before. This is the maternal data set. We looked at it again. We saw this data set when we talked about does smoking lead to smaller birth weights? Okay, we're going to take the same data, but we're going to look at a different statistic. So in this case, right, we're going to the baby birth data set. And so this right now, this is an actual sample. Okay, so this is different than the San Francisco data set, which was the complete population of San Francisco public city workers, right? This is a sample, right? A sample, because if you think about the population is mothers, pregnant women, right? So the whole population is obviously not all of the pregnant women. So this is a sample. So this is going to be a sample, right? So we don't have ground truth in this case. And the statistic, the parameter that we're going to be interested in is the mean maternal age. So on average, how old are these mothers? Okay, and so we're going to do an estimate by bootstrapping the mean maternal age. Okay, and then we're going to generate a confidence interval of that parameter from there. Okay, then this is different because we don't actually have a ground truth. But hopefully I've convinced you by looking at the San Francisco, where we did have the ground truth, that there is some confidence in the process itself. Okay, so let's take a look. And again, this is our baby table. And then the thing that we'll be interested in this column here is maternal age from there. And if we look at the histogram from that, you can see that there's kind of a interesting kind of distribution from here. It kind of looks like it peaks like around, somewhere maybe like around 26, 27, and then it kind of tails off from there. And so we don't have to just eyeball it. We can use the power of Python to give us the mean. Okay. So what we're doing here is we are just computing the mean from after we extract the maternal age column down up here. Okay. And so our sample mean, and again, right, this data is a sample, is about 27, right? So eyeballing was actually pretty good. Okay. So now let's get a confidence interval about the mean. And so again, we're going to follow the exact same paradigm. We're going to write a little helper function that's going to do one bootstrap mean. And so remember, this is our sample. And so this is going to be the table. And so we're going to use the birth table, and we're going to sample, because this is our sample. We're going to sample all the rows because we want to resample, right? Because there's not taking a sample from the population. This is the sample from the population. So this is going to be the resample. This is what we're looking at right now, is the resample of our sample, and the birth are our sample. So because we're doing the bootstrapping resampling, we're going to have replacement be true from there. And then now we want to just extract the maternal age again. And just like we did up here, we're just going to take the mean from there. Okay. So this will generate this will do the bootstrapping process, right? It will sample for the same number of times as the rows, right, of our data. And this is a nice technique, using the number of rows as opposed to hard coding the number of rows in, because, for example, maybe you decide you wanted to eliminate smokers, right, from that, and created a new table of births, right? By using kind of the num rows, no matter what the number of rows is, it's going to follow any changes to the table from there. So that helper funder generates one statistic for us. And again, this is just nothing new here, nothing new. This is going to, now that we have our one statistic, right, we're going to run our accumulator pattern to collect 1,000 of them. And then we're going to look at the 95 confidence interval. So we're going to take 2.5% on the left, 2.5, and then 97.5 from there. And then once we have all of that, then we can plot, right? So we have our bootstrap means, and we're just going to turn it into a table, and then take the histogram of that. And then we'll just look at the intervals, and then we'll look at the sample mean as well from there. Okay. And so now if we look at this, so the sample mean, right? So if you remember what the sample mean is, this was the mean that we took from our sample. That was the thing we got up here. And so this was the sample that we got. This is the mean that we calculated. And then from the bootstrap process, we've generated this 95% confidence interval. So we've gotten the high, the low, and the high. And and so what we're saying about that is that we expect, because of our process, again, we don't, this is, we don't know what the ground truth is, but we expect, because we have faith in our process, that ground truth would be between 26.89% and 27.58%, that the ground truth would fall somewhere in this range, somewhere in the gold bar. Okay. Any questions? Any questions about that? Okay, so with great power, and the bootstrapping technique is a very powerful technique. With great power comes, you know, great responsibility. And so it's good to know kind of what exactly is this technique doing, and kind of knowing that allows us to kind of, you know, make sure that we're using these methods appropriately. And so I'm going to ask a couple of questions about the confidence interval. So, right, so kind of what we looked at, we saw that by our calculation, our approximate 95% bootstrap confidence interval for the age of mothers in the population is 26.9 to 27.6 years. Okay, so now the question I want to ask you is true or false? True or false? About 95% of the mothers in the population were between 26.9 years and 27.6 years old. Is that a true or false statement?
It's false.
Yeah, and so it's if we go back and actually look at if we look back at the bootstrap, yeah, if we go back to the beginning, right? This was the histogram of the maternal age, right? So what was that question asking? That question was asking 95% of the mothers in the population were between 26.9 and 27.6, right? So another way of saying that, are we saying about 95% of the mothers fall between, kind of right where my cursor is? And you can see that that is very clearly not the case, right? If you look at kind of the percent per unit, right? This is that narrow band was about a year, and each of these bounds are much larger than a year. Each of these bins, and you can see that the percent per unit, right, is like 7 for that. So very, very, very obviously that is not what we're saying. So where is the confusion coming from here, right? The confusion is coming from, or why maybe sometimes you may think that. Well, the confusion is that this is not, we're not saying anything about the distribution. Remember, the distribution, our confidence interval is over a statistic. And what is the statistic? We are estimating the average age in this, that is in this interval, right? So we're not saying that all that all mothers are between that. We're saying that the average of the population falls within that range. It's our estimate, right? We're giving an estimate. We're giving an estimate. We feel like, with 95%, probability that the actual statistic, the actual population average age of the mothers is between 26.9 and 27.6, right? So that's the average age across the entire population. Not that, that's just saying, if we gave a midterm and the average was 85, and if I took a sampling, right? That's just, it doesn't mean that all grades kind of fell, within that range. It just means that the statistic that we calculated. Okay, so I think that one I think was a little clear. This one I think is a little more subtle. Okay, this is another question here. So the same thing, right? By our calculation, the bootstrap interval for the average age in the population is from there. So true or false? Okay, there is a 95% probability that the age of mothers in the population is in the range. The average age is in the range of 26.9 to 27.6. Okay, true or false? I want you to discuss this a little bit. We won't take too long, but let me create some breakout rooms for there, and then let's give. I want you to talk about that first. So I'll send you just for like about 2 minutes from there, and then we'll come back. make a consensus?
I think so.
Yeah. What did you guys come up with?
So if the wording's the same, we're 95% confident that the actual value we're looking for is within that range.
And so you would go with true.
Yes, true. Mm-hmm.
And I see why you get this. I see why you get this, and this is exactly why I kind of asked the question. And it seems very logical to kind of think about this. I feel like this is a little bit about kind of weird semantics from there. But I bring this up to kind of drive home the point. So the answer is actually false. And the reason why it's false is it's actually very subtle. Okay. And because and when I kind of first saw the question, my gut reaction, I think most people, their gut reaction is, especially the way I've kind of described it is that, yeah, that it means there's a 95% probability. But if we look specifically at what the question is asking, right, we're saying that we're asking about the probability that the average age of the mothers in the population is in the range. And that's kind of the fatal kind of flaw in this argument, because the average age of the mother in the population, it's unknown, but if we knew it, it's not a range. It's actually a statistic. There's nothing random about it. And this gets to the fact of when we talk about a probability, there has to be some randomness involved with that. Like the probability of rolling a dice, the probability of flipping a coin. There's a random element in it. Mm-hmm. And in this case, the statistic is actually a statistic. It's unknown, but there is no uncertainty with it. And so this gets to the value of is that probability, that 95% is our confidence in the process from there. And so, I feel like this was a little bit of a tricky question. This was kind of, I feel like it's a little subtle, it's a little sleight of hand sort of there. But, but it's good to kind of tease that out. In what do we mean? Where is this confidence? Where is this probability coming in? It's the probability in the process, not in the statistic itself from there. And so what does this really mean, right? And so this gets down to the point of just in the interest of time, because I've sent you into the breakout room, so hopefully you had good, I won't send you into the breakout room for this from there, right? So if it's not the probability that the statistic falls into their range, so what are we actually saying? What we're saying is, remember, right? What are we doing through the bootstrap process? The bootstrap process, if you think about it in terms of inputs and outputs, as if this were a function, right, of some black box. The thing that gets the input to this whole black box is our sample. The thing that gets spit out is an estimate of our statistic. It's an estimate of our parameter. And so that's the thing that gets, spit out of this whole process. And so what we're saying is that by our estimate, the thing we spit out, that the average age of the mothers in the population was within this range. We don't know what the truth is, but the average age, so because the average, because of the statistic, is going to be somewhere between these two. And that the process that we've generated, that we've used to generate this, right, this whole bootstrapping process, is going to be correct about 95% of the time. Okay, so so we're using a process to spit out this number, this range, this interval, and that confidence interval, that confidence is our confidence in the process. It is a confidence in the process that number that we spit out is correct 85%, 95% of the time. That the ground truth, if we had some way of knowing it, was within that range, was within our confidence interval 95% of the time. Okay, does that kind of resonate? Does that resonate with you guys? Or are there questions about that? The confidence is in our process, that the process that we use 95% of the time, the ground truth lies within that interval. And that's all we're saying, and we're not saying anything more than that from there. Okay? And we'll get practice. We'll get practice using this from there. Okay? So that's the technique. And so then the question is, right, it's a very powerful technique, but again, it's just the technique, right? You see, it's just an algorithm. You can just treat it as a black box, and you can use it on anything, right? You will get an answer. If you give it a sample, you run it through the process, you will get an answer. You will get a confidence interval out. But are there cases, is there cases where it's not a good idea to use the bootstrap, right? The bootstrap is not going to tell you, hey, maybe you don't want to do this, right? It's just an algorithm. It's just going to spit out a number from there. And so that's, you know, I think the thing I worry about is that once we learn a technique, you know, you know, so it's a model, right? We're building this model. And so there's going to be conditions where the model applies and there's conditions where it doesn't. And so it's worth highlighting the cases when using a bootstrap is not a good idea. Okay, so, right, you know, note it was not a coincidence that a lot of the statistics we were looking at for was kind of these medians. Using a bootstrap when you're trying to estimate very high or low percentiles or min and max, it's not a good fit. And you can think about why this is, right? If you just think about the process itself, where we're taking that initial random sample, right? And presumably we have, you know, taken our sample large enough that we've captured the spirit. But if you have like a very long tail distribution, or you have some outliers, it's you know, if you have like a small percentage that are kind of dominate the sort of things, our sample may not capture them, right? Our sample may not capture them, or if you're trying to go for min and max, you know, that can kind of get us into trouble from there. And then kind of, you know, kind of tangentially related to kind of what I said about that, if there's some parameter that is affected by rare elements in the population, right? If you have like one data point that is actually going to greatly affect, right? So like it was a very maybe bimodal distribution or something like that, or you just had like a really big kind of black swan event type thing that really affected the actual truth, right? Because then it really comes down to the fact of did you capture that in your original sample and in the resampling, right? If that, you know, so even if you caught it in your sample, the resampling, because you're sampling with replacement, there's no guarantee that if there's like some single event or some single data point that greatly influences, is that it's going to necessarily be captured from there. And, you know, a good way to kind of, you know, a sanity check, right? So, you know, these are good rules of thumb to go by, but a sanity check that I hope that you always do when you're kind of doing the bootstrap is that you look at the probability distribution of your statistic, right? You're computing some statistic, and when you do the bootstrap, you're going to do it 1,000, 10,000, so, you know, however many thousand times. Look at the distribution of your statistic, okay? If it's bell-shaped, thumbs up, like we have some confidence that this is going to be good. If it's not, that's a sign that maybe the bootstrap isn't going to be, you know, going to be representative of that. And then the last thing is if your original sample size is very small. Okay, remember, this is all predicated on that the sample that we take is an accurate reflection of the greater population, and that happens when that sample is large and random. Okay, all right, this is a perfect place to stop. And we'll pick up kind of this idea of using confidence intervals for doing testing next time. All right, we have a couple of minutes. We have a couple.
Okay, yeah, so for today, we're gonna review a little bit of, I think, Bootstrap. Okay, so we were on topic 19 last time. So let me share my screen. Okay, we're on topic 19 last time, where we're yeah, where we started talking about confidence intervals, okay? And then of course the confidence interval, oops, down here. Yeah, the confidence intervals that we have been talking about is under the hood of doing Bootstrap, okay? So I guess it's a good chance for us to take a moment and then think about and review a little bit about what Bootstrap is doing. And then of course, from that, how to do confidence interval. And we're gonna wrap everything into a case study, which is the second notebooks here, okay? So remember the Bootstrap, okay? So if we come back here, okay? The Bootstrap, okay, if we do a quick review over here, okay? So Bootstrap is necessary or useful, I guess necessary in this case, that if you only have one sample, okay, but you want to figure out certain uncertainty or like the variability of your statistic, and then if you only have one sample, one way you can still create a repeated sampling scheme is to sample at random from the original sample with replacement. Okay, so that's what we mean by this line, okay? And in practice, as you know, in Python, what you do, right, is you do the sample method with replacement, okay? And then we also make sure that, remember, the Bootstrap sample should have to have the same number of values in the original sample, okay? So like whatever n that you're doing, okay, should be fixed as the size of the original sample. And these two conditions here are done, like I said, by the dot sample method, and then make sure that you do replacement is true. Okay, so that I think is what we have introduced, how Bootstrap is done. Okay, and then also if we come back to topic 18, the slides a little bit. Again, just to also talk about why Bootstrap works. Okay, so we have a population, right? Unknown out there, we don't know what it is. Okay, we have a sample that can be a good estimate, right, of the population. So the Bootstrap works in a way that we repeatedly sample out of the original sample with the same size. Okay, so you're able to come up with a bunch of resamples. Okay, so they will be slightly different, of course, from the sample that you have. Okay, but they're overall similar to some degree. Okay, and then let's just say we're interested in, just like what we did before in the hypothesis framework, let's just say we're interested in a particular statistic, like the mean of the, in this case, I guess the compensation. Okay, let's just say we're interested in the mean of the total compensation. Okay, and for us, each resample, right, we're able to compute the total compensation, the mean of it, right? And then we do that again through a loop, okay, for a large number of times. And then from there, we're able to come up with the empirical distribution, right, of the statistic, which is the mean, okay? And then from there, we can do our hypothesis as usual, okay? So this is a quick review-ish, okay? But like I said, we will be doing a case study, okay? How to use confidence interval, like how to come up with the confidence intervals in the first place, okay? And then how to understand what a confidence interval mean. And then lastly, how we can use, instead of a p-value, but use confidence intervals for testing. Okay, so this is the case study that we're gonna center on, okay? But I just want to also just bring us back a little bit to, like, say, the graph. Last time we covered what is a 95% Bootstrap confidence interval. Okay, so in practice, what we do, like I said, you get a bunch of resamples, right? And then from each resample, you're able to get a mean. Let's just say that's the statistic that you're interested in, right? Let's just say we do it for 10,000 times, okay? And then we're gonna have 10,000 resampled mean, okay? And then from there, we are able to construct a confidence interval. Okay, so if we come back to what we mean by confidence interval, okay, we are figuring out the 95% confidence interval out of the 10,000 mean statistics that we have computed. Okay, so this is where, if you remember, what the percentile is going to be useful, right? Like the confidence interval, we're trying to get the middle 95%. Okay, so if you remember last Tuesday, we talked about how to do the percentile and how to understand percentile. In percentile, you first sort the data, right, from the increasing order, right, like smallest to largest, okay? And then whatever percentile that you compute is sort of like counting how many is below that value, okay? So that is why if you want to get, so remember the Bootstrap confidence interval, right, is based on all of the Bootstrap samples and the statistics that you're able to get. So let's just say we have 10,000 means, okay, of the total compensation, okay, and then we store them up, right? We store them from the smallest to the largest, okay? And then if I get the cutoff point at 2.5% at the lower end, and then the 97.5% at the upper end, then with the percentile method, right? So then I will be able to narrow into the middle 95%. Okay, and then that's how actually in Python, how we're gonna get that confidence interval. Okay, so what this is telling us, just to repeat and review a little bit, is that this interval is the interval bootstrap estimates of a parameter. Okay, our goal is still about the total, like the average compensation in the population. Okay, it is computed based on random bootstrap sampling. Okay, and 95% is called the confidence interval because, well, you can do 98, 95, 97 things like that, whichever you want to do. And the higher the confidence level, the wider, okay, the confidence interval. And you could imagine, right? Like for 95%, we get 2.5% to the 97.5. If I want to get a 99%, I do from the 0.5%, right, to the 99.5%. So that I'll be able to include the middle 99. Okay, so as this value increases, the width of the confidence interval going to increase. Okay, not surprisingly. Okay, and this, as you will see, that will be related to how we're going to use the confidence interval to make decision. Okay, so if you remember, for hypothesis testing, we have those p-value calculated, right, based on the repeated sampling that we do, and then we have those cutoff points like 5% to mean statistically significant, right? 1% to be highly significant, statistically significant. So those values can also be translated into doing confidence intervals, and then confidence interval can then be used as a hypothesis testing tool. Okay, so we're going to see that. And lastly, it's very important, okay, to understand what a confidence interval means. Okay, so this graph, if you remember, is a example, okay, of the median. I think $1 million, probably, I think, out of the total compensation as well. Okay, and then what we really mean by confidence interval, okay, especially 95% confidence interval, is that, let's just say this red vertical line, that's the population median. Okay. And then every time, right, we take, every time we take a confidence interval from a bunch of bootstraps, we are able to come up with one interval, like as one of the lines over here as the yellow one, okay? So what this is saying is that a 95% confidence interval, what it does for us is that if we were to repeat the whole process, okay, for coming up with a confidence interval for like 100 times, then roughly about 95 of them gonna cover the true population median. Okay, so this is why, if you remember, okay, we try to highlight, can you use a CI like this, right? Like what is the real meaning of doing a confidence interval? So it is very important. So first of all, it's usually about either like average age or like a parameter, right, of the data. Not so much about like all of the data points. Okay, so that's one thing very important to know about the confidence interval. Okay, also is how to understand it's not about like a 95% probability that the average age or average mean will be actually in the interval. Is that if we are able to do this for a large number of times, 95% of the time that we're able to capture the parameter. Okay, so that's why, just to final review over here, which is what a CEI really means. Okay, so in this case, by our estimate, the average age of mothers in the population was somewhere between these two values that we calculate from this set of bootstrap samples, and that our process of estimation is correct about 95% of the time. Okay, when we say that, this is saying that, okay, if I now go ahead, do another set of 10,000 bootstrap samples, and then I get another 95% confidence interval, then I do another. If I do that for a large number of times, then about 95% of the chance I will be able to cover, like using my interval, right, to cover the truth. Okay, so hopefully this is a useful review, but like I said, now let's come to the confidence intervals for testing, and then we will make sure that everybody's on the same page about understanding confidence intervals, how to do them, and then one step further is how to do the testing. Okay, all righty. So the example that we're going to do, okay, really quick over here. The example we're going to do here is how to use CI for hypothesis testing. Okay, and we are actually going back to, I think, the baby's data set about mother smoker and the age. So the null hypothesis, okay, is the population average is a particular value, okay? The alternative is not that value, okay? So this is the setup of the case study that we have, okay? So the cutoff point, remember, if we do hypothesis testing, we can always use p-value, right? Let's just say we're using p%. It could be 5, could be 1, but generically, we're going to use p. So this is when you're using p-value to do hypothesis testing, okay? However, now we're introducing the new method of using confidence interval instead of p-value to compute or to test your hypothesis. So the way to do it, okay, is to construct a 100 minus p% bootstrap confidence interval for the population average. Okay, so putting into practice, if p is 5, okay, so let's just say you want to use the p-value cutoff point of 5%, that's equivalent, okay, of creating a 100 minus 5, which is 95% bootstrap confidence interval. Okay, if p is 1, then you're doing a 99% bootstrap confidence interval. Okay, so this is the method, okay, the first step to construct the confidence interval in the first place. So still, even though you're not going to use the p-value, right, to do your hypothesis testing, but you still need to know the cutoff point for the p-value that you want to achieve. So once you know that value, you're able to know what is the confidence level of the confidence interval that you're doing. Okay, then the decision process goes this way. If x, okay, whatever the value that you're trying to test is not in the interval, you're going to reject the null. If it is in the interval, then you do not reject the null. Okay, so remember, in the usual case, okay, when we're using the cutoff point to do p-value, okay, if p-value is really small, if you remember what we really mean by p-value is that under the assumption that the null is true, right, the p-value tells me the probability of how likely it is to observe something as extreme as my data. Okay, so in that histogram, if you remember, right, it's usually in the tail, right? And we're trying to compute the probability that way to get the p-value and then use the cutoff point. Similarly, okay, for confidence interval approach, what you do is that I still get the interval, I still get the histogram, right, from the bootstraps, okay? And what I do is instead of computing what is more extreme than my x, okay, what I'm computing is I'm computing an equivalent to the cutoff point, like 100 minus p% confidence interval, right? And I'm going to check if my x value is in it or not. Remember, if I'm doing like a 95%, it's middle 95%, right? If my x is in it, that is saying that under the assumption that the null is true, my x is quite similar to what I can get, okay? But if it's x is outside of the interval, let's just say it's over here, okay? Then that would be the case that, well, under the assumption that the null is true, I will have a really low chance to observe my observed data. Okay, so it is really equivalent to some degree about the p-value. Okay, but this is the alternative method that you're able to construct a confidence interval in the first place, and then just make the decision determining whether x is in the interval or not. Not, then you're going to reject it because that's showing that your x is very extreme, right? And then if it's in the interval, then you do not reject the null because that's telling you that under the assumption that the null is true, it is likely for you to observe something as extreme as x. Okay, so this is the general approach of what we're doing. And like I said, it's probably much easier to go through it using a case study. Okay, so we're gonna do this in Python. Okay, and let's do that. Okay, so this is going back to the baby data set. Okay, we're looking at the mean maternal age of the mother. Okay, so the data set is a little bit, I guess it's a little bit more than 1,170 observations. Okay, so this is a sample. Okay, don't forget, this is a sample. Okay, we don't have a population here. So what we're gonna do is we're gonna use a bootstrap method to create a confidence intervals, and then from there make hypothesis testing decision. Okay, so if you look at, okay, the histogram of the maternal age of mother of the original sample, this is how it looks like. Okay, and if we take a look at the mean of the sample itself, is a little bit over 27. Okay, so this is the data that we have. Okay, and like we know now, because we don't have access to the population, right? The only way that we're able to make inference in this case is through bootstrap. Okay, we're going to bootstrap a large number of times of bootstrap samples from the original sample. From each, we're going to compute a mean, right? And then we're going to construct a confidence interval out of that. And then we're going to see how we're going to make decision. Okay. All right. So to do that, always good practice. So this hopefully starts to like make sense to you all that, well, if you're doing for your project as well, you probably want to write a few functions as well. And you could even just borrow what we have covered in demos, in homeworks or labs, because some of the, as you can tell, like many of the functions work in a very similar way, right? Like this one, this is what we call by a one bootstrap mean, okay? Of course, you have to change the name of the data set a little bit, right? But otherwise, everything is pretty straightforward and similar to, like, say, if you change this into a different setting, but your goal is still to get one bootstrap mean, the function can work in a very similar way, okay? So I guess let's talk about the function itself first. So this is, again, trying to get one bootstrap mean. So what we do, right, this is a bunch of nested function. Okay, so let's take it slowly. We work with the births data set, right? That's the data table, right? We do a sample with replacement, remember? Okay, and then we're only gonna collect all of the values of the maternal age, okay? And then that gives us a array. And then on top of that, we do npeak mean, which is gonna give you the average. And then this whole function itself can do one bootstrap mean for you with this birth data set, in particular, the maternal age column. Okay, so if I run that, well, nothing will happen. I only really define the function, okay? But just so you know, like I said, a lot of times like this general method works in all of the other contexts as well, right? So one thing, if you want to, let's say for a project that I want to do a bootstrap confidence interval for, I don't know what kind of data sets you guys are working, but I remember there's one about penguin, like different types of penguins. So let's just say like I wanted to know about the bootstrap confidence interval of the, I don't know, the number of particular penguins in an area, let's just say that, right? And then if I want to do it, then this kind of approach is very general, right? You take the data set, right? You use the sample method to get a bootstrap sample, right? And then you only care about, like, say in here, maternal age, but in there, maybe just the number or the count. And then you take the mean. Okay, so I bring this up mostly because right now the function is written in a very specific way. It's for the birth data set, right? And then of course you also have to know that the name of the column that you're doing your bootstrap mean with. But one way to really quickly make it more general, I just want to do a quick, not a demo, but just like a quick exercise. I'm creating a new cell in here. So one thing to make it general is that, right, I can ask the user to input the data table, right? I can also ask the user to input the column label, right? In terms of what is the numerical variable that you're trying to work with. Okay, so if I do that, let me just add underscore so it's easier to do. If I now replace data table births, right, with data table everywhere, remember? And then the column label that I'm doing, right, with the column over here, notice that the label now in this case needs to be a string, okay? So if I do this, then I can actually use this right now, like use this function in any other context if I want to do a bootstrap mean for a different data set and then from any kind of column that over there that I will be interested in. Okay, so just keep these general ideas in mind. Like I said, I think as you start to do more, especially getting to the inference part of your final project, I think this starts to make more sense of why you want to write a function as general as you can. So later on you can pass, right? You can pass the data table in, you can pass the column label. This is very similar to what we have done, if you remember, about shuffling the labels, right? Before we're trying to do a hypothesis testing over there. We're trying to write it very generally, okay? You can just really pass in the data table, pass in the different labels that you want to work with. So in the end, this function can be used in many other places. Okay, all right, so that's about that. So let's just say that we're gonna use this one bootstrap mean method, okay, the function that we wrote, okay? So what we do is we write a for loop, okay? So don't forget, you always need to start with the empty array, okay? And then you determine how many times you wanna do it. And then every time, as you can see, we run this one bootstrap mean function, okay? So from there, we get a new mean, and then we append it into the original. So we're able to, okay, this is gonna take, okay, pretty quick, okay? So this all will have run the simulations for 1,000 repetitions, okay? And notice that here we define a left to be the 2.5 percentile cutoff point, okay? And then the right we're doing the 97.5 percentile cutoff point. Okay, so getting those two values, as you could imagine, is providing us the confidence interval. Okay, we want the middle 95%, so I'm doing from the left 2.5, from the right 97.5, so I'm able to get the middle 95%. Alrighty, so let's look at how it looks on the graph. Okay, so the histogram, okay, is very similar to what we have been doing, right? You do the simulation for a large number of times, right? Each time you get the summary statistic or test statistic that you want to do, right? And then you graph it out. What's new here, as you can see, is that we're adding a yellow bar at the bottom, okay, in addition to the middle mean point. Okay, so what we're doing is that we're getting the bootstrap means, right, in the histogram, but then we also remember the left and right, the two objects that we're able to compute earlier, we're trying to add them as a, as a bar down here, okay? So you're able to visualize it. And we're also printing them out, right? The hour sample mean, if you remember from up here, without, like before doing bootstrap, is 27.28, 23-ish, okay? So that's the sample mean. And then if we do it for 1,000 times of the bootstrap sampling, we're getting a 95% bootstrap confidence interval for the mean, which is about 26.89 to 27.57. Okay, so, well, next, as you could imagine, we're going to try to use this to test hypothesis. Okay, but before going forward, any quick questions about how we're doing all of this in the first place? And yeah, like, I guess why we're doing this, as well as how we're doing it. Like questions, comments, or concerns? Okay, all right, yeah, again, feel free to speak up or just type in the chat. And so also, before we move on, just want to say that in the past, right, we didn't really use a confidence interval, right? We didn't cover what a confidence interval is. We didn't know how to compute it, but we do know, if you remember, if like a data set, like a data point comes along, we're able to sort of graph it on this graph, right? And then trying to figure out the p-value. So I just want to make the analogy here, because what we're doing right now is not that different from before, okay? In the past, we are able to come up with like a 90, I should say, like a large number of bootstrap or simulated samples, right? And then we get this test statistics. So we're able to get empirical distribution of it. And then we're able to compare our observed statistic to all of this, because all of this are simulated under the null. Okay, and then we're using that as a decision-making rule. Here, instead of doing that p-value computation, we're coming up with confidence interval. Okay, and like I said in the slide, we're saying that if X, whatever you're testing for, is not in the interval, you're going to reject it, right? If it's in the interval, you're going to do not reject it. Okay, and again, the reason is because if it's in here, then that means that whatever the value I'm testing for under the null, under the assumption that the null is true, it is pretty common to observe that, right? But then if it's not in there, outside, okay, that is actually equivalent to a really small p-value, if you could imagine, right? If you do the computation actually, then that gives us the hint or the evidence saying that under the assumption that the null is true, it is not very likely to observe my tested value. So that will give me the evidence and the confidence to reject the null. Okay, so that's why if you come down here, okay, if we try to use bootstrap confidence interval hypothesis testing, okay, this is following very similarly to this general framework that we've written down over here, okay? We're gonna come up with a hypothesis, the null, the alternative, you're gonna determine the cutoff for your p-value, and then from there, you're gonna construct, which we already sort of did, right, of the confidence interval, and then the next, or the remaining task is just to perform the interval, perform the hypothesis testing procedure itself and make the decision. Okay, so our method, okay, we're going to determine cutoff. Let's just say it's p%, right? And then we're going to construct a 100 minus p% bootstrap confidence interval, and then make decision based on whether X is in the interval or not. All right, so let's just say my null hypothesis is that the population average mother age is 30. Okay, my alternative hypothesis is saying that it's not 30. Okay, and then, well, if you remember, for the 5%, the 95% confidence interval that we did, which is constructed, okay, let me just run this one more time, okay, which is constructed based on actually equivalent to a 5% cutoff point, right? And then we computed, this is slightly different because you remember every time is is a random draw, right? For the 1,000 different draws. So it might be slightly different from the 1,000 that we did up there, but pretty close, I would say. And let's just see. This confidence interval goes from 26.88 to 27.57, okay? And 30, which is the X that we're testing, is outside of this range, right? It's outside of this interval. So based on our decision-making procedure, we're gonna reject the null. Okay, and if you imagine where 30 lies, well, it's going to be way beyond, I think, where the plot is, because the maximum over here is 27.6-ish, right? And the range only goes from 26.8 to 27.6. So I have to say, I think 30 is already beyond this page itself. Okay, so 30 is very unlikely, as you can see, out of this bootstrap sampling. So we're going to reject the null. Okay. The other one is, what if I'm making my confidence interval slightly longer? Okay, what if I'm using a wider net or wider net to cast these true value over here? Okay, so if we're going to do a cutoff point of 1%, which means that we're going to do a 99% confidence interval. Okay, not surprisingly, it's longer, slightly longer, not so much, but longer than before. Okay, because now we're covering the middle 99% instead of the middle 95%. Okay, so as that value increases, you're going to have a wider interval. So it is more likely for you to cover, right? To cover the test statistic because it's wider. But in this case, even at the 1% or 99% bootstrap confidence interval level, we're still going to reject the null, okay? Because 30 is still outside of this confidence interval that we're able to get, okay? So this is generally the procedure of doing confidence interval for hypothesis testing, and in particular, we're doing it through the bootstrap confidence interval. Okay, so all of this, I hope, starts to make more sense to you. Okay, why we're doing bootstrap in the first place and how we're doing it, and then how we are doing cutoff p-value with equivalent level for the confidence interval, and then why the confidence interval works in the way that we're talking about here is for decision making for hypothesis testing. Okay, so any questions, comments, concerns? How the data is, how the process is done in the example? Anything? Okay, alrighty. If not, I'm gonna